Right, a little bit of history on magnetism. Okay, magnetism. We know that we have written proof that they knew about magnetism as far back as the Greeks, at least that far. They may have known something about it earlier than that. That's just as far back as I know, anyway, that they have proof. The Earth, oh, by the way, there are natural magnets, which is what some of the Greeks found anyway, is called lodestones. They are iron-bearing ore that you can dig up, and it has a weak magnetic field. Okay, so they will affect each other or affect other things that have iron in them. Okay.
So they're natural magnets, or
yeah, they're natural magnets. You can dig them up from the ground.
So they're not, they weren't charged over the years or something.
Well, yeah. What's happened is that in iron-bearing ore, if it cools real slow, like it's warmed up and cools real slow, that the Earth, it'll line up with the Earth's magnetic field, and that's how they become a magnet, a natural magnet. All right, that's how magnets are born. All right.
All right, somebody else.
Come on. Tired of asking you all to be quiet. Okay, the Earth in the 1600s was discovered to be a magnet. Okay?
Obviously.
And in the late 1700s and the early 1800s, there was a lot of work on electricity. Like, for instance, Ben Franklin, 1700s, Faraday, late 1700s, early 1800s. A lot of work with with electricity, and at the same time they noticed a lot of similarities between electricity and magnetism. Okay? So, what are some of the similarities between electricity and magnetism? Think static electricity.
Charged particles.
Okay, you've got charged particles. What kind of charged particles? What kind? Yeah. What kind? You've got positive and negative, right?
Yeah.
All right. What's the similarity to magnetism?
Positive and negative. Poles.
Yes, poles. How many poles? Two. What are they called?
North and south.
North and south. Okay. How do plus and minus relate to each other? What do they do to each other? Okay, what do north and south do to each other?
No, attract.
They also attract, right? So opposites attract here, and opposites attract here. And if I have a positive and a positive, they repel, and north repel, right?
Yes.
Okay, do you know why they call it north and south?
Because that's what they
And not plus and minus or something like that?
That's what they believe.
Because they already had north and south.
Yeah, had to do with the Earth.
The north attracted towards the North Pole.
Yeah, here's the North Pole, here's the South Pole, so here's where Santa lives, here's where penguins live.
And polar bears, they hug off.
And polar bears live up there.
They don't live in the south.
No, penguins.
Penguins down here,
What did cockatoos?
puffins up here,
And
or polar bears, and Santa, and elves,
Dinosaurs.
the North Pole.
and dinosaurs. So they have found dinosaurs down here, but none up here, because there's no land. All right, now, so if you have a natural magnet, or a man-made magnet, if you prefer, which is what a compass is, right? It's just a little magnet in there on a spindle, so it can spin around. And so what we say is when we're sitting right here on the Earth and we have our little compass, the red side is usually the north side. We call it the north side because it points
Towards the north.
towards the north.
So there's something you
But wait a minute.
In reality,
It's a south.
If the north side of the magnet points north,
Then it's a south.
that means that this is really, the Earth is a huge magnet, but that's the south pole and the north pole of the Earth's magnetic field, right?
We actually need more because that's confusing, We can forget that.
So our compass, the north side of our compass, points to the geographic north, which means it is attracted to the south magnetic pole.
Is that what it actually is though?
Well,
Yes.
maybe the compass is just
Right.
the south needle is attracted to the North Pole.
But they call it north, so we're stuck. So actually what we have is, this is south magnetic pole of the Earth up here. Okay? But we don't don't need to worry about that. Okay, relax. It's alright. You can just call it whatever you want to call it. We just know that our magnet points north, right?
Call Sandland up there.
Alright.
Oh, that's
By the way, the Earth's magnetic field, is shifting. Y'all know that?
Yeah.
So what, like the little thing is turning?
Yeah, so like if you look at the Earth from the top, okay, so like here's the North Pole right here. And you have like Alaska over here, and you got Canada over here, and you've got Russia over here, and like Sweden and Finland and all that over here. I guess it's still in Canada, but it's moving. It was moving when I was young. It was moving south, more towards the
It was
equator.
already over in Canada?
Yeah, it's not at the North Pole. And now it's shifted, and it's rocketing across this way, towards Russia. Rocketing. Yeah, how fast? Like yards, every year. But like in the last, I forget how many 100 miles it's shifted in the last 10 years. It's pretty far, actually.
Wait, miles?
The Earth's magnetic field
That's
shifts.
more than yards per year.
So,
I don't remember. I'll have to look it up. I don't remember. But in your lifetime, it may end up over in Russia.
So like if you're standing like above it in Russia, like the really cold part of Russia, and you're trying to find your way back.
Yeah, so like if you have a compass and you're
Say
standing
north
at
to
magnetic north,
It's gonna be pointing.
then the compass tries to point down. Okay, so like if you hold the compass sideways, it'll point down. So like if you're at the North Pole right now, it points out towards Canada. Okay? So I guess it was in Tampa, I think Tampa, Florida, they just had to shut down the airstrip and then repaint the numbers on the airstrip because the airstrips have the magnetic compass headings on them. So that when you fly, you know I'm flying at 18 degrees, and so I'm going to land on runway 18. Actually, it's 180 degrees. You land on runway 18. Okay? So they had to swipe the number off and put a new number down. So it's shifting. Anyway, not a big deal. Not a big deal. If you go through the Earth's geologic history, you dig a core down through the Earth, and you look at the different lodestones in it, where the iron is in the core sample, you'll see that the magnetic field has shifted through time. So right now we have the South Pole, South Magnetic Pole up here. It's been down here before and it's flipped before. So we may be in a region of when it's going to flip.
How does that happen? How
Yeah,
does it
my
move?
question was going to be, does anybody know how that happens?
so
Why that happens? Why do we have a magnetic field at all? Equilibrium.
Right.
It's like the moon does not have a magnetic field, but the Earth does. It has to do with the fact that we have not only an iron core, but a molten iron core. It has to do with you have to have moving charges. And the moving charges create a magnetic field, which we'll talk about in just a minute. So it's the fact that the Earth still has a molten core that circulates, that creates our magnetic field. Okay? So like the sun and, let's see, which planets don't have a magnetic field? I don't remember. I don't remember if Mars has one or
Why
not.
would the sun not have one if it's completely melting?
The sun has one. The sun and all the gaseous planets have one because they have all these convection currents.
Yeah,
And,
that's
yeah.
what I think.
All right, at any rate, so just a little bit of history. In fact, that's one of the things that they have so much trouble with the sun is trying to figure out how its magnetic field works.
Wait, is
Okay?
that why Pluto's not a planet anymore? Because it doesn't have a magnetic field?
I don't know if they know if Pluto has a magnetic field or not.
No,
But no, that's not why.
They changed it because when they discovered that it's too cold to send about, they needed to find what.
Yeah, because they're discovering even larger things than Pluto, even farther out in that what's called the Kuiper belt, and so they had to decide how they wanted to label all these things. They decided to label them non-planet. All right. Now, there are some other similarities between these things. There's another big similarity. One is that the electric field decreases as you get farther away. In fact, remember, the electric field decreases with 1 over 4 pi epsilon naught Q over R squared. It reduces with a 1 over R squared as you get farther away. Magnets do the same thing. You've all played with magnets before, where you take magnets and you kind of push them around, or the closer you get them, the bigger the force is, right? The farther away, the less the force.
Try really close to base.
Yeah, you try and get it really close and they keep twisting away.
Yeah, like.
Alright, magnetism has the same 1 over R squared relationship. Okay? Now there are some major differences between electricity and magnetism. One of them being, you can have an isolated electric charge. It's possible to have a plus or a minus.
You can't just have a north and a south.
Yeah, you cannot make just a north or a south. For instance, if you have a magnet that has a north side and a south side, if you break the magnet in two, attempting to make a north and a south, what's called a monopole, a single pole. Yeah, what you end up with is a north and a south here, where the north and south is weaker than the north was up here before, and you end up with a south and a north over here. You can't split them. Okay? Now, another similarity.
Wait, so does that mean if you break this thing all the way down to where there's like one atom left, it'll have a north and a south pole?
That's correct. That's correct. Which it turns out to be a quantum nature of matter, which they call spin, but it's not really spin. They just call it spin because they didn't know what else to call it. I'll describe why it's spin.
Oh yeah, the off-ball diagram thing was like the up and then down.
Yeah, spin up and spin down. Yeah, it's an intrinsic magnetic field. I'm not sure exactly why it occurs necessarily. They just know that it is. It's like they don't really know what mass is yet, but they just know it's there. Okay, it's like mass, charge, and this spin.
I don't think they should really worry about that.
Okay, everybody, shh, listen. All right, electric fields. You have electric fields. They exit out a positive and end on a negative, right?
Yes.
Magnetic fields are similar. They exit out a north and circulate back around to a south, but there is a difference. They don't start on north and end on south like they do here. They start on positive and end on negative. But magnetic fields exit north and enter south, but then continue through. And they never have a beginning or an end. They're always a loop. Okay?
That's deep.
It is kind of deep. All right, so there's no beginning or end to a magnetic field. It's always going to be a continuous loop of some kind.
That's scary.
Wait. So can you drive backwards? Can you go south and then like that?
Well, inside the object, it goes from south to north. On the outside, it goes north to south. That's correct. So you can draw it like this normally, but then it'll inside the object, it goes back around.
Okay, from south.
Okay. All right. So there are some differences. Now, the similarities between the two made scientists look for, well, first of all, think that there was a connection between the two. All right? And then they started looking for the connection between the two.
I have a quick question.
Yeah.
How do the magnets that you can turn on and off work?
Oh, it's an electromagnet. I'll get there.
All right.
All right. The connection between electricity and magnetism was found by accident by actually a professor, Hans Christian Ørsted. He was a professor. In the story that I heard, at least, what he was doing was he had a lab that he was doing a demonstration in a big lecture hall, the way they did it back in 1820. And so he had this long wire or current carrying cable or wire of some kind, and he was showing them something about electricity, and they turned on the switch. When they turned on the switch, current would go through the wire. Well, he happened to have a compass nearby, and he noticed that the compass deflected when the current went through the wire. Now, we have no idea if anybody else saw this before him. We just know that he spotted it and his brain went, bing! Wait a minute. Compasses are affected by magnetic fields. We just turned on this wire with current through it and the compass deflected. If the compass deflected, that means that there must have been a change in the magnetic field. And so they flip the switch on and off. They notice that the compass switches, it moves, it deflects, and then you turn it off and it goes back to normal. They said, okay, that means that this wire somehow or another is producing a magnetic field. All right? Now, from that early beginning, and in fact, here's how it looks actually, because he went through and did a little bit of study on it and published it, so that's why he gets famous on it.
Must have been actually one of the students who did that in the teaching section right front.
That happens sometimes, yes. Yes. All right, if this is my current carrying wire like this, what he found is that he could make a table. All right, and this wire comes up through a hole in the table. All right? And then he puts compasses around it like this. And he notices that the compasses will point this way.
Towards
All right?
That's weird.
the circle grinder.
Yes, so it's in a circle pattern. Ha ha ha. In a continuous loop, right?
Yes.
No beginning and no end. So they don't point towards the wire or away from the wire like they would if it was charged, right? They point around the wire. And so he says, well, we've got this thing, this magnetic field, and by the way, still in books they use B for magnetic field, and I believe that comes from, so we just talked about this last time, right? B for compass. What's compass in Spanish?
Brújula.
Brújula. I can't say it.
Brújula.
Thank
Probably
you.
write it down.
That's right. I can't spell it. I can't spell English. Why would I spell in Spanish?
B-R-U-J-A-L-A.
What is it? B-R-U-H-N? Oh, no, sorry. B-R-U what?
J.
J?
U.
U?
L-A.
L-A. All right. Spanish word for compass, Spanish coming from Latin, and so that's probably where that comes from. B for magnetic field. So we have a B field. Magnetic field. Okay, so you'll hear me call it a B field all the time. That's a magnetic field. All right, so we have a B field that goes around a circle. Now, that's as far as he got pretty much. He described the shape of it, described how you could create it, but it took 11 more years.
Before he got shot.
No, 11 more years before anybody could definitively say how these things are produced. Okay? And that was given to, is it Faraday? Faraday, Heinrich Hertz. So Michael Faraday, Heinrich Hertz, and shoot, what's the American? Henry. All kind of came up with the idea at the same time, but Faraday published first, so he gets the credit. Okay, everybody. So, what did Ørsted teach us? Ørsted taught us, or discovered, that you can create a magnetic field if you have moving charges or a current. Because a current, remember, is moving charges, right? So as long as a charge is moving, you create a magnetic field. So think about that for a second. You take a balloon, you rub it on a cat, you get it all charged up, because it's easy to charge it up. Alright, you take your charged balloon, you run through the room. Shh. Do you have a charged balloon?
Yes.
Is it moving?
Yes. It's current.
That's current. Are you producing a magnetic field?
Yes.
Why, yes, you are. Okay? So if you have any kind of charge and you move it around, however you want to move it, you'll create a magnetic field. Kind of crazy. Alright? Now, what is the shape of this magnetic field? Okay? Yeah, the shape is circular. Okay? Alright, so circular. How do we describe this shape? Alright.
Infinite loop.
You ready? We're going to call on our first right-hand rule.
No.
Okay, now this is that's alright. This is a different one. Okay, it's not the forced one. It's an easier one. Okay, here you go. Our first right-hand rule looks like this. Okay, there's your hand. It's your, which hand? Right hand. Here's your thumb. Your thumb is in the direction of positive current.
This is the.
And your fingers curl around in the direction of the B field. Okay, you ready?
Yeah.
So your thumb points in the direction of the current, and your fingers curl around the direction of the magnetic field, curl in a circle. Notice that the magnetic field is in a circular shape with no beginning and no end, right?
Yeah.
Okay, so let's do this one right here. If the current is up, extend your right hand,
This.
grab the wire with your thumb pointing in the direction of the current, and your fingers curl around. So which way is the magnetic field? It's this way, right? It's only counterclockwise or depends on which way you look at it, right? Okay, so we have three-dimensional issues to worry about in magnetic fields, in magnetism. Okay, so let's do it this way. What if the wire is coming straight towards you? If the wire is coming straight towards you, all right, everybody, you got to do this. The wire is coming straight towards you. Is the magnetic field clockwise or counterclockwise?
Counterclockwise. If the charge is coming still.
If the current is coming towards you, and we're talking conventional current,
Counterclockwise.
that's going to be counterclockwise, right? So, everybody,
We look like idiots.
on a two-dimensional board, we have to decide how to draw this. So here's how we're going to draw it. This is an arrow. I'm sorry, it's a vector. There's my vector. If this vector is pointing to the right, no problem. If it's pointing up or down or to the left, no problem. But what if it's coming out of the board? If the vector is coming out of the board, you see the point of the arrow first. So if it's coming out of the board, this means out. Either a dot or a dot with a circle around it. That means out of the board. Okay, into the board would be the tail feathers. Either an X or an X with a circle around it. Either one. Okay? So the tail feathers means it's going away. The dot means the point is coming towards you. Okay? Alright? Now let's see if we get it. Because this is challenging.
Wait, there are also left-hand rules, right?
Yes, but we are not there yet.
Oh.
Okay, if we have current going this way, remember we define current as positive charge movement, right? Okay, if my current is going to the right, then up here, above the wire, which way is the magnetic field?
It's like
It's like coming this way and that way.
That's right, it's coming this way and then this way, right? So if you looked at it from the end, it's going around it like this, correct?
yes.
Okay, but if it's going around it like this, that means at the top, above, it's coming
Down.
out of the board at you. Your fingers are curling out of the board here
Exactly.
and into the board here, right? So your magnetic field above the wire looks like dots, and your magnetic field below the wire
That makes
looks
sense.
like X's. Does that make sense? Because that's challenging for a lot of students sometimes. So make sure you understand that.
Your fingers, the points of your fingers are dots.
Yeah, the points of your fingers are dots, and then I don't
rest
know,
is
knuckles going in.
Dots.
Okay? If the magnetic field, here, B,
Recycling.
B, B. Okay, if the magnetic field's going like that, B, sorry.
Current's going
Into
Which way's the current going?
into the
You have
bowl.
an X. You have an X.
Into
You have an X.
Okay, it's going away from you, X is away, right? Because your fingers curl this way, right? Now, notice if the current is going that way, then it has to be coming out of the board and then into the board, right?
Yeah.
So it's coming out of the board and then into the board, right? Okay. That's kind of challenging to see at first. Three-dimensionalness, right? But you can do it. The best way to do it is to really look stupid and curl your fingers around and that sort of thing, right? Okay. What about this? Because this is on your e-homework. What if I have a wire here that has a that has a current coming that way, and I have another wire here which has also current coming that way. Look at this spot in the middle. Which way will the magnetic field be at that spot in the middle?
There won't be zero, yeah. Because they're counteracting. They're both moving the same ways.
Okay. Here's my suggestion.
Yeah.
So they'll collide and they'll be like a supernova.
I'm going to call this the green one. Which way is my green magnetic field circulating?
That way.
Is it circulating
Counterclockwise.
this way or this way?
That way.
Okay, this way, right? Okay, so it's circulating this way. So here's my circle around. At this point, which way is the magnetic field then? Because remember,
Up.
vectors must be a straight arrow. So it's got to be around this way, but tangent and straight up. Very good. So that's the magnetic field for the green one. Okay, what about the blue one?
Down.
Down.
Why down? Isn't it going the same direction? Isn't it both going this way?
Yeah, it's going to be.
Ah, but you're on the other side of the circle, right? So this one's circulating around this way as well, right?
Are they the same charges?
That's a black eye.
Yeah, let's assume that they are the same current and your same distance.
So it's zero.
So this one is going to be circulating around this way. In fact, it's like this, right? They're going around, but I'm only interested in this one spot right here. So these should cancel each other out, correct?
Yes.
Yeah.
Yes.
All right. What if I had a wire like that and a wire like this, and I looked at the spot in the middle?
Will be
It'd be super up.
Super up. Okay, here's this one over here. That one's going to be up. And here's the one over here. That one's going to be this way, right?
So it's going to be up.
So it's going around this way, but it's going to be up as well. So you're going to have a super up.
Super up.
I like that. Hey, I believe you have an e-homework assignment that looks something like this.
No, we don't.
What if you have a current here? Uh-oh, this one's about dead. Current here, a current here, a current here, and a current here. And I'm looking for the magnetic field in the center.
Okay.
Current, current, current,
All the same current.
current, all the same current, all the same distances. All right. So I'd like for you to figure out what's the direction of the magnetic field right there for that one in the center.
That made me nervous.
Go, go, go.
Well,
It's like
Okay, well look at this one.
Okay, yeah.
This one right
It's
here.
talking about the Y coordinate.
Yeah, I'm talking about that.
Which way is that one circulating? Clockwise or counterclockwise?
Clockwise.
Okay, clockwise. So at the center point right here,
It's like-
the tangent would be in that direction. That's my magnetic field from that one. Okay, how about this blue one?
It's the other way. It's like
Which way is that circulating? Clockwise or counterclockwise? Still clockwise, right? So which way is that one going to point?
down
Towards the one that's right
down
there.
right.
That way?
Yeah.
Down and to the right. So we have that one. And since we have the same current and the same distance, these should be the same, right? Okay, how about a green one? Which way is the green one going to point?
Also the same direction as the clockwise. No, wait, upward, upward,
Like
upward.
that. It's gonna go.
Okay, which way is it circulating?
Up. Well, no.
Yeah.
Yeah. It's towards the
So it can only point that way or this way, right?
It's gonna go up.
Which way?
Up and right.
upright.
Up to the right? I agree. Because it's clockwise, right?
And then that one.
Okay, and then how about this red one right here?
The same as the blue.
Which way does that circulate? Around. But does it go clockwise or counterclockwise?
Counter.
Why counterclockwise?
Like this.
Because your thumb points out and it goes this way. So which way is that one going to point?
Towards the blue.
one.
Towards the blue one.
So that's twice the magnet.
So what happens to this one and this one? Okay, those two cancel and these two add up, right?
Yeah.
Super.
So it's a double, right? So this will be double what one of these was, right? Okay. That's kind of challenging, figuring that stuff out, right? Figuring out the directions of those. But you can do it. It just takes, draw some pictures, draw those circles, and remember, it's going to circulate clockwise or counterclockwise, and it's always going to be tangent to the path, either with, clockwise or counterclockwise. Okay, so the question is, all right, that's fine. We know the direction now, but what is the strength of the magnetic field? Okay, here you go. Magnetic field strength for a wire. Okay, for a wire that carries charge. Now, Jonathan, for an infinite wire. Okay? Now, when we say an infinite wire, we actually talk about these in Physics C, right? Okay, when we say an infinite wire, we just mean the wire is long enough so that, and you're close enough to it, so that it appears to be really long compared to how close you are to it.
I was going to say, 19 centimeters isn't that long.
19 centimeters is not infinite. But if you're 1 centimeter away from it, that's essentially infinite. Okay, and here's our equation. We derived this in Physics C, but in Physics B, we just give it to you. It looks like this. It's mu naught over 2 pi I over R. Okay? Let's talk about the things we know first. B is magnetic field strength. I is current. So I equals current in amps. What would R be?
Radius.
R would be the radius that you are perpendicular from the wire.
And me top?
Which one?
Whichever wire you're interested in.
Wait, what?
So like for instance, I would calculate this for 1, 2, 3, 4 wires. Actually, I wouldn't, would I? I'd calculate it for 1 wire and they'd all be the same strength, right? Because they all have the same geometry. Okay? Radius in meters. Okay, 2 pi is 2 pi.
Mu naught.
So mu naught, okay, you ready? It is called the permeability, or vacuum permeability, or permeability of free space.
Oh, that's a constant.
It's a constant, very good. The constant is actually 4 pi e to the negative 7th Tm over A. Okay, we know what A is, right? A is amps, M is meters, T is something new. T is Teslas. T equals Tesla. 4 pi e negative 7. It's a constant.
I remember that from that. You remember that?
Yeah.
What was the guy's first name again?
Nicola.
Nicola. Nicola. I don't think it's Nikolai. I think it's Nicola.
It's Nicola.
Nikola
Like
Tesla.
Milan.
No, he's not Russian. He's Croatian, actually.
I think there's
Okay,
a
wait.
Russian
The
who's
radius is amazing.
Nicola.
So B is measured in Teslas?
Yeah. Magnetic field.
And so, everybody, look what happens. This is in Tesla meter per amp. That's amp, and that's meter. So, what is B field measured in? Tesla.
Wait, so isn't mu naught over 2 pi just another constant? Why don't they have their own symbol?
Very good. So, mu naught over 2 pi. What will that be? That's 4 pi e to the negative 7th divided by 2 pi. That ends up being 2 e to the negative 7th Tesla meter per amp. So if you want, you could just use that constant right there if you'd like.
Okay, and the radius, how is that again? What is the radius?
Okay, the radius is, here in my 3D picture, it's easier to see. That's that radius away. However far away you are from the wire.
And they'll give us that?
They'll have to give that to you, or they'll give you the magnetic field and you'll be able to solve
What was it? What was it? How far away were you from the wire?
Yeah, so like if this is my wire, like right here. Here's my wire. That's my radius.
Okay.
The perpendicular distance from your wire. Okay? Okay, so here you go. Here's a problem that shows up occasionally on the test. What if I have a wire this way and I have a wire this way? And I want to know, let's say the current here is 2 amps and the current here is 1 amp. Make it easy. And let's say I'm interested in this spot right here where this is 3 meters and this distance from here to here is 2 meters. I don't know why I didn't put it there. 2 meters. And I want to know what is the direction of the magnetic field right here. Okay? Now, if I had given you a charge, a positive charge and a negative charge here, and I asked you what the direction of the electric field was here, then you would figure out the electric field from one charge and then the other charge, and then you'd add them as vectors, right?
Yes.
Okay. Same thing occurs here. Handle them one at a time. What is my magnetic field like because of this wire at this spot? Okay? Can we figure out the magnetic field strength?
Sure.
It's going to be mu naught over 2 pi I over R. Okay? What's mu naught over 2 pi? It's 2e to the negative 7th, right? What's I? 2 amps. What's my radius? 3 meters. So what do I end up with? 4/3 e to the negative 7 Teslas, right? So that's 1.33, is that right?
Yeah.
Okay, 1.33 Teslas. Okay, but it's a vector. Which way is that vector?
It's coming out.
It's
at
coming
that
towards you.
point.
Everybody,
Yeah, it's coming out.
you can't get this right unless you try it. Which way is the magnetic field right here because of this wire?
Popping out.
Thumb down, fingers curl. Which way are your fingers pointing?
Towards me.
Out. So this is a out vector of that strength. Okay, now let's do the brown wire.
Oh, that's an in. That's an in.
Why is that an in?
Because
Because
it's
it's
like
pointing in.
Ooh, because your thumb points this way and your fingers curl into the board down here, right? When your thumb here on the axis.
We just did that.
Ooh, so I'm going to have an in here, an innie and an outie.
Yeah, belly buttons.
All right, well, what's the magnetic field strength here? B equals mu naught over 2 pi I over R. Well, that's 2e to the negative 7. My current is 1, and my radius is 2. So I get 1e to the negative 7
in.
Teslas, but that's in. So which one wins, brown or blue?
Blue.
Blue. So what's the net magnetic field at that spot?
0.33 -7 Teslas out.
The answer is going to be 0.33 e to the negative 7 Teslas out. And that's your answer. That's a pretty challenging problem, actually. You can do it, though, right? It's not that hard. I mean, you
That's
can...
gonna suck. I can tell.
All the directionality stuff is what messes you up.
It's Valentine's night,
Okay. Hey, everybody, what if you do this? What if you have a wire and you do this? You put a battery like this, and the battery goes around like, or the wire goes around like that, so the current goes this way, and then this way, and then this way, and then this way, and then this way. So that's the direction of your current.
So the center has a bunch of outs and the outside has a bunch of ins?
Okay, that's my question. What's the direction of the magnetic field in the center?
Out.
Why out?
Because of the current, the way
Because your fingers point out, and out,
because my
and
hands
out, and out. Okay, you've got to get that. Okay, do you get that?
Yes.
All right, can you go over that again?
Do you get that?
So thumb points this way, so it's out, 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 out on the Oops, out. So it's all dots.
Thumb goes where the arrow goes.
So there's your magnetic field on the inside. What's your magnetic field like on the outside?
About.
It's all going to be a bunch of ins, right?
Oh.
Hey, now look. That means if you take a wire with current in it and you loop it around and loop it around and loop it around and loop it around all in one direction, that's the direction of my current. What kind of magnetic field do I get here?
Massive out.
I get a bunch of out magnetic field, and the more loops of current I have, the more of these I just keep building up because I end up with more and more and more current, right? And so you're able to make a large magnetic field. And yeah, what you do is it looks like this from the side. Loop it around, loop it around, loop it around, loop it around. And what you end up with is a magnetic field that goes through. And it looks just like a magnet.
Smashing electrons.
Okay. Daniel, you said how do you make these things? That's how you make them. So you take the wire and just loop it around, and then you hook it up to a battery, and it'll produce a magnetic field that looks just like a magnet. And if you put an iron core in the middle, the iron will line up with it, and you'll produce an electromagnet.
Is that the concept of like smashing things together really fast?
You can use these electromagnets to accelerate things with charge. We'll talk about that. If a moving charge, like a current in a wire, can produce a magnetic field, and that can affect a compass, can a compass or a magnet, which produces a magnetic field, affect the wire?
Of course.
Of course. All right? And that's the right-hand rule that we learned real briefly last class period. Okay, what we've learned so far is just how a wire produces a magnetic field. Okay? Okay, what we're going to do now real quick is figure out how does a magnetic field affect a wire? All right, so I'm going to make magnetic fields in blue.
Are those not going like
So which way is my magnetic field pointing? Into the board. Okay, here's my wire. My wire has current in it. Remember, that's positive current.
Isn't that impossible because the top one should be pointing in?
Good question. This is an external magnetic field, like the Earth's magnetic field. And then I just have a wire with current.
Okay.
Okay? All right, remember, here's our right-hand rule for force on a wire. Actually, it's magnetic force on a wire. Here's our right-hand rule for that. Okay, you ready?
Loser.
All right. Your fingers curl in the direction of the B field. Your finger points in the direction of the current, and your thumb points in the direction of the force. Remember, BIF. BIF, as you look at the palm of your right hand. Okay? So everybody, I want everybody to stand up.
I'm trying to write this down.
Everybody stand up. Take the appropriate finger and point it in the direction of the current. Yeah, appropriate finger. Okay. Now, remember, your hand's going to be like this, right? Okay, curl your fingers, once you're pointing this way, curl your fingers in the direction of the B field. Which way is the B field?
In.
Into the board. So rotate your hand so that you have your index finger pointing in the direction of the current, and your B field lines pointing in the direction of the B field. Okay, remember your thumb is always perpendicular. So which way does your thumb point? Up. So which way is the force on the wire?
Up.
Up. Okay, let's see if you get it.
That's a movie.
All right, here is my new current. Here's my new wire with current in it. Okay, which way is the force on this wire?
Left. Left.
Left.
That way.
It's left.
That way.
Look where my thumb is pointing.
Towards
Right.
Bruin. Towards Bruin.
To the
Towards
other
Bruin.
right.
Towards Bruin.
Yeah. Towards your opposite of right. Current up, B field into the board, thumb points to the left. So the force is to the left.
I still got it right.
All right. Okay, let's see if we get it. New B field.
Okay.
Where's the wire? Ow, my leg.
Which way is the magnetic field?
Where's the wire?
Out.
Which way is the magnetic
Out.
field?
Yeah.
Which way is the magnetic field?
Out.
Out. All right, there's my current. There's my current. Current 1 and 2. Which way is the force on 1 and 2?
Down.
Down.
Like this.
One is
One
down.
is down.
Here. There.
Two is
Here, just
that
do
way.
this.
Okay.
Now, if you find that your arm doesn't work that way,
It does.
if your arm doesn't work that way, then my suggestion would be, when this is on paper, is to rotate your paper so your arm doesn't break. Okay?
My arm works.
Or rotate your body. Current this way. B field is this way. So the force is down.
Force is that way.
He's just.
Okay, which way is the force on this one?
Perpendicular to it, but towards this way.
Right.
That way.
Perpendicular up.
Which one?
That way.
This one or this one?
To the
So that we count.
Current this way. B field out of the board. So it's going to be up and to the left.
Yeah.
All right, everybody sit down. Okay, I got one more for you.
Oh, we can sit down. Give it a shot.
In the board.
Okay, which way is the force on this wire?
Into the board.
Into the board.
Into the board.
Yes.
Okay, current up.
Yeah.
B field
That.
this way.
So X.
So into the board.
Spin your fingers.
My hand is so useful.
Why are you doing that?
I don't know.
Hi to you too.
Hi.
Current up.
Just like 8 people at this table.
B field into the board.
Oh.
I'm sorry, B field to the right. Sorry, current up, B field to the right. Okay, so the force is going to be this way, correct?
It's like 9 people at this table.
Okay, everybody, you ready? What if my current is this way?
What? You can't have the field and the current in the same direction.
What do you mean I can't?
Yeah, you can.
Wait.
I mean I can't line a wire up with the Earth's magnetic field and send current through it?
Well, okay, yes, but
Directly in front of me. I want to out here.
Still into the wall?
I want to see it.
Okay, which way do you point this finger?
That way. That way.
Which way do you curl these fingers?
That way. So it's
I
down.
feel like I'm really throwing
What do you mean? It could be
What does it stand for?
anywhere, right?
Chop it down.
Okay, here's the deal.
Chop this down.
Here is our equation for magnetic force in a wire.
Magnetic force is 0.
It is I, L, cross B. Remember cross product?
No.
Okay. Cross product is sine theta, so it's I, L, B, sine theta. Or a lot of times students will remember this as they'll call it Bill sine theta. B-I-L sine theta. Okay?
Wilson.
Now, everybody. Hey, whenever you have a dot product or a cross product, this angle is the angle in between these two vectors. What's the angle in between magnetic field and current?
90.
90. Well, for this one it's 90. What's it for this one?
3 degrees.
0. Theta equals 0 here. Theta equals 90 here. What's the sine of 90?
1.
1. What's the sign of 0?
0.
0. So how much magnetic force do I get on that wire? 0. They have to cross each other. What if I had one at an angle?
Then
Then it would be
about half.
somewhere between maximum and 0, right?
What is L?
See the real spark in that.
Okay, L is the length. Oh, good question. Hey, everybody. Everybody knows what I is. That's the current. B is the magnetic field strength. This is the angle in between. L is the length of the wire. So, like, for instance, right here.
The angle
So the
between
longer the wire, the better?
Yeah, well, the more force you get. If this is my magnetic field, then this would be my length. But what if I have just a little bit of length of wire like that?
smaller force.
Then that would be just the length there, right?
Wait, so what's the angle? The angle between what two things?
The angle between the two vectors, which is the current and the magnetic field.
So shouldn't that one be the same?
Well, not necessarily. Like, for instance, what's the angle between the current and the magnetic field here? 90, because my current's in the board and my magnetic field is out, so it's 90, right?
Yeah.
Technically, that field's not related to that current.
That's correct. It's an external magnetic field. Thank you.
That's why I was saying you couldn't have them.
Oh,
It's not, it would hinder.
Yes.
One of them would hinder the other, right?
yes, yes. Now, I think I've answered most. Have I answered most of the questions? There may be one about the force between two wires. You might have to look that one up in your book.